atomic packing factor. ABF. I took a glance at the syllabus this morning, and I think that that's what is on the list. Does anybody have a syllabus handy? Make sure I'm forgetting something.
Yeah.
That's it? Okay. So atomic packing factor. That is the ratio of the volume of a metal that is, we could say volume of a unit cell, that's occupied by atoms divided by the volume of the unit cell. So it's sort of like the percentage of a metal that's actually metal as opposed to just vacant space. So you might remember that for a body-centered cubic unit cell, body-centered cubic metals, 4R was equal to the square root of 3 times A. And there were 2 atoms per unit cell. And for FCC, 4R was equal to the square root of 2 times A, and there's 4 atoms per unit cell. So anybody know off the top of your head what is the volume of a sphere?
4/3 pi r cubed.
Say it again?
4/3 pi r cubed.
You got it. 4/3 pi r cubed. So the volume of the volume that's occupied by atoms, if I have 2 atoms per unit cell, then the volume occupied by atoms will be equal to 2 times 4/3 pi r cubed. Yeah? And the volume of a cell, we know that the unit cells are all, the length of every side is equal to A. So volume of a cell will be equal to A cubed. And that'd be equal to, let's see, A is 4R over the square root of 3 cubed. Okay, and for FCC, the volume occupied by atoms would just be 4 times 4/3 pi r cubed. And the volume of the unit cell, A cubed, that would be equal to 4R over the square root of 2 cubed. So the atomic packing factor then is going to be, in this case, 8/3 pi r cubed divided by 4r over root 3 cubed. And here this is going to be 16/3 pi r cubed. Okay, and here, 4r over square root of 3 cubed would be 64r over 3 times the square root of 3. And that's r cubed. And this would be 64r cubed divided by 2 square root 2. So, the atomic packing factor for BCC, let's see, that's the volume occupied by atoms. 8/3 pi r cubed divided by the total volume, 64 r cubed over 3 square root 3. So that's 8 pi r cubed times 3 root 3 divided by 64 r cubed times 3. So then cancel these 3's, and r cubed. Take this 8 out and make this an 8. And so I get the square root of 3 pi divided by 8. So what does that equal to? What's the square root of 3 pi divided by 8? What's that value? So I get 0.68. So that means BCC metals are 68% matter and 32% nothing. Piece of steel, iron. You pick up a piece of iron, and 2/3 of it is matter, and 1/3 of it is just nothing. The space between the atoms. Okay, what about FCC? Here we've got 16/3 pi r cubed divided by 64 r cubed over 2√2. So that is 16 pi r cubed times 2√2 divided by 64 r cubed times 30. Do I have everything there? Yeah. So I canceled the 16 and make that 64 a 4. Okay, and I could get rid of this 2. Make that just a 2. So I've got square root of 2 pi over 6.
And then the 68% represents of a unit cell or just of the material itself?
Oh, the material, because the material is unit cells in 3D space. So in this case, we get 74%. And it turns out that FCC is called a closest packed metal, or closest packed system. And what that means is we can't get atoms any closer than that. You can't get an atomic packing factor any bigger than that. Or you can't get one any denser than that. If you have a wire, an iron wire at room temperature iron is BCC. And you string it across 2 sides of a furnace. You leave a little bit of play. And you heat it up. When you get above 812 C, iron changes from BCC to FCC. And so it gets more dense, and the wire shrinks at one temperature. And then you heat it up, and I don't remember this temperature, 17 something C. It changes back to BCC and goes limp again. Lots of metals will change crystal structure with temperature, but the one that we know and we've experienced the most, of course, is iron, because iron is like sort of the foundation of metallurgy. There is one other closed pack system in the metal crystal structure that we're not going to talk about. Yeah, Lorenzo.
So you said that BCC metals are like less malleable than FCC metals?
Oh, I wouldn't say they're less valuable. No.
Malleable.
Malleable?
Or
BCC
softer.
are less malleable, yes, for sure.
So is that showing that with APF?
Partly, right? Because if the packing factor is smaller, then the atoms ultimately are closer, and they can have a bigger influence on one another as far as permanent deformation. But yeah, I would say that it does have some We'll get to the real reason, the big reason, when we get a little bit deeper into the crystal structure. So this other crystal structure that is closest packed is a hexagonal crystal structure. This is why we're not going to spend too much time talking about it. But if you imagine a hexagon where there's an atom at every corner of the hexagon, and under that is a triangle with 3 atoms that fit right into that hexagon, and then below that another hexagon in 3D space. That's the hexagonal close packed system. It's not as easy to draw, it's not as easy to analyze. But because it's closest packed, there are metals that are closest packed, HCP, hexagonal close packed, that have properties very similar to FCC. I'm thinking zinc is HCP, and it behaves a lot like the softer metals that are FCC. Okay, so that's our atomic packing factor. All right, theoretical density. So last time we did calculate the number of atoms in a unit cell and the volume of a unit cell. If we know, for a metal, if we know the volume of a cell and the mass of the cell, mass over volume is density, we could calculate the theoretical density. So let's think about what that would be. We know density is mass over volume. So let's say mass of a unit cell divided by the volume. Okay, well, that would depend partly on crystal structure, yeah? So I'm going to say, let X equal the number of atoms per unit cell. All right, so then the mass of the unit cell is the number of atoms times their mass. So that would be X times, I'm going to call M, the atomic mass. And that's usually given in, everybody know, units for atomic mass? Involves moles. Grams per mole. And I want grams. Wait, is it grams per mole? Yeah. So if this is in grams per mole, and I want to get rid of that, this is actually units of atoms per cell. Sorry, this is so small. X atoms per cell times M grams per mole. So now I have atom grams per cell mole. Woo. And I just want grams per cell. So is there a number that gives me the relationship between the number of atoms and the mole of atoms? Avogadro's number, right? So I want 1 over, I'm going to say N sub A is Avogadro's number. 22, and the 23rd atoms per mole. So I got it. I'm just gonna make this neater. I'm not changing anything. I'm just gonna make it neater so you see how the units are canceled. So this is, Ensobe is atoms per mole. Okay, so now the atoms cancel, the moles cancel, and I have the grams per unit cell. Yeah? Now I want the volume of unit cell. Well, that's easy. A cubed per cell. But rarely can you look up the lattice parameter A. So let's go ahead and convert that to atomic radius. So I need a number that says y is equal to, well, let's see here. R is equal to the square root of 2a for FCC, and 4r is equal to the square root of 3a for BCC. And the volume is a cubed. So let's make this number square root of 2 or square root of 3. That's going to be what y is. I want to have an equation that works no matter what the crystal structure. So for FCC, y is equal to square root of 2. For BCC, y is equal to the square root of 3. Okay, so the volume of the unit cell, A cubed. And A, let's see, 4R, Y, A. 4R is Y, A. Yeah. Just like that, except I'm going to cube it. Get rid of all the A's. So R is atomic radius. And A cubed, A. This one's called the lattice parameter. So as long as the unit cell is cubic, this only works for a cubic unit cell, density is going to be equal to x times y cubed times m over Avogadro's number times 64 times r cubed. And density is usually grams per cubic centimeter. I'll have grams in the numerator. This R needs to be in centimeters, but usually it's not. usually R is given in picometers. Used to be nanometers. But now we can see things that are much smaller, so it's picometers. A picometer is 10 to the 12, there's 10 to the 12 picometers in a meter. So 1 meter equals 10 to the 12 picometers. And I'm going to want centimeters. 1 centimeter is 10 to the 10 picometers. So I need to put that conversion in there when I solve. So let's do an example. I have a list of,
Why do they use grams per cubic centimeter as a unit instead of grams per cubic meter?
they use grams per cubic centimeter.
Why don't they use meters?
Oh. They,
'Cause I feel like usually.
maybe it'd be too small a number. I mean, grams per cubic centimeter is always somewhere between 5 and maybe 50 or so. So if it was grams per cubic meter, we'd always have to have I don't know.
Okay.
Nobody's ever asked that question. I think it's probably convenience.
Okay.
I mean, cubic centimeters is a common unit in volume as well, right? I mean, sorry, in that, and in medicine, CCs,
Got it, yeah.
right? So that could be, but it's a good question, I don't know. In many ways, centimeter seems like much more of the standard measure than a meter.
It's just, yeah, usually, I mean, in every other class, you just convert everything to meters for the
Yeah.
base unit, and then you just.
Yeah, well, and we have to if we're going into Pascal, you're right,
Mhm.
but not here.
Okay.
Okay, so I got some hypothetical metals. Let's see. All right, so let's try and find out what is the density of this is Sullivanium. Well, when I just pick mine first. So I've got atomic mass of 90.7 grams per mole. And I've got an atomic radius of 137.6 picometers. And it's an FCC metal. So if it's FCC, then that means X is equal to 4 and Y is equal to the square root of 2. All right, so let's see, density is going to be 4 times 2 to the square root of 2. M 90.7 grams per mole. 6.02 10 to the 23rd atoms per mole. 64 r cubed. 137.6 picometers, and here we gotta do something here so we don't forget. We're gonna have to say 137.6 cubed picometers cubed, so we don't forget to cube that number. And I know that there are 10 to the 10 centimeters per picometer, and that's cubed. So,
Professor, if the 10 to the 10 centimeters, shouldn't that be switched to the picometers?
I just, hold on, I see an error and I need to fix. Here. Okay, sorry, Ella?
That's what I was saying.
Oh, okay. So, I want to take 10 to the 23rd and 1 over 10 to the 30th. So basically, 10 to the 23rd divided by 10 to the 30th. And just make that 10 to the negative 7. I think I've done everything I need to do, so now I've got grams, moles have canceled. This number here actually is atoms. The atoms have canceled, moles have canceled. And I've got grams per cubic centimeter. Okay, so we need 4 times 2 root 2 times 90.7 divided by 6.02 times 64 times 137.6 cubed and 10 to the minus 7.
Question.
Yes.
Why is it 2 root 2 on the top? Why is it just root 2?
Because this is y cubed and y is root 2. So root 2 cubed is 2 root 2.
Okay.
Good?
You should have root cube, got it.
Yeah. All right, so what do we get here? What we should get I didn't fill it in. Let's see what we get. I get 61.5 on my first attempt. Now I get 10.2.
That's what I get too.
That's what you get?
Yeah.
Anybody else get 10.2? No? I'd like to have more than 2 people agreeing on a number.
10.2.
10.2?
Yep.
Okay. So the density of whatever this hypothetical metal is 10.2 grams per cubic centimeter. If I was going to name the thing, the error that most often shows up, it's forgetting to cube that number. All right, so essentially we have density, atomic mass, atomic radius, and crystal structure as our unknowns. So let's try a problem where we don't know the crystal structure and we're trying to identify it. All right? Now, one way to do that is to guess and solve for density and see if you get the number that you're given. Or we could find out what is xy cubed BCC and what is it for FCC and solve for it. So for BCC, x is 2, y cubed is 3 root 3. So that's 6 root 3. $10.4. And if this is FCC, x is 4, y cubed is 2 root 2, so that's 8 root 2. 11.3. Those numbers are kind of close together. It will, the number you get, if it's a correct number, will be very close to one or the other. So let's see if we can find the crystal structure of a metal. All right, tabacolium. All right. Let's say the density is 9.9 grams per centimeter cubed. And the atomic mass is 102.3 grams per mole. And the atomic radius is 144.3 picometers. So I know then that 9.9 grams per centimeter cubed is equal to xy cubed times m, 102.3 grams per mole, divided by Avogadro's number, 6.02, 10 to the 23rd atoms per mole. And this is atoms per cell. Avogadro's number, then 64, then atomic radius, 144.3 picometers cubed. And I want that to be centimeters cubed, so 10 to the, what is it, 10 to the 10 picometers per centimeter cubed. So x, y cubed is equal to, let's see, my goal, I got the grams have canceled, centimeter cubed, picometer cubed, moles are canceled. So I'm just going to deal with the numbers. So xy cubed is equal to 9.9 times 6.02 times 10 to the 23rd times 64 times 144.3 cubed times 10 to the minus 30. All of those things divided by 102.3. So let's see if we can get one of those two numbers. 2. So this must be FCC. Now again, this feels like on their equation sheet, you'll get this equation, but not the terms defined. If it feels like I'd rather guess that it's FCC and put the numbers in here and solve it and see if I get that number, and if I don't get that number, well, if you don't get that number, it might be a math error. You still probably need to test the other number, right? But you could do that. You don't have to use this method. But it is faster, for sure. And similarly, the unknown might be R, or the unknown might be M. Do that the same way. Okay? Theoretical density. Okay, let's talk about crystal defects, and then we'll take a break. So we know what this crystal structure looks like, right? ECDFCC. So, without drawing these defects, just talking about it, just introducing the topic, and when we talk about them specifically, I'll draw them for you. There's 3 sort of groups or classes of crystal defects. One group are called point defects. And there's 2 types. But this is just a point in space. It's a one-dimensional defect. It could be that where there would, like, let's say I've got FCC. It could be that where I would have my, we could call it solvent atom, I have a foreign atom, I have a different atom. Instead of all iron atoms, maybe that's a nickel atom. Okay, that's one kind of defect, it's called an impurity. And it's at the atom level, so it's not like something that didn't dissolve in the hot molten metal. This is an atom that is different than all the others. The other kind of defect is where an atom is missing. There's a place for an atom, and there just isn't an atom there. And that's called a vacancy. So the 2 kinds of point defects are vacancies and impurity. And that's all I'll say about that until we get deeper into point defects at the end of this lecture. Okay? So it's possible that there isn't an atom where there would be one. It's possible that there's a different atom. I can tell you that when you calculate theoretical density, you'll always get a higher density than you'll measure. And partly that's because we're assuming that these unit cells go off in all directions without interruption, and that's not true. But also that we're assuming that every place on the unit cell has an atom. And because there are places that don't have atoms, the density is less. Right? The density could be more because of a foreign atom, but there's never so many foreign atoms that it would change the density. So the density can be less because of a defect. That's actually one of the things that led the search for why are we measuring a different density than we're calculating and finding these defects. Okay, so that's the first group, point defects. The second group are called line defects. They're 2D. And the best way to think about them right now is, it is because of these defects that we can plastically deform anything. Because these defects move during permanent deformation. So imagine that you've got a runner, a long, heavy rug, right? And you need to move it 3 inches in one direction. And it's very heavy, and it's very long. And you tug on one end, and there's too much friction between them for you to be able to move it. But it's possible to move it without magic, and that involves exactly doing something like that, right? Where you, and then pull. And what you've done is you've created a defect. You've created a place where there's no rug touching the floor. And then you're just moving that down. So that line that you've created where there's no rug touching the floor, that's a dislocation by what we call defects. We create, those are created in a metal and then moved when it's deformed. So that's what a line defect is. And we'll talk more about it, and I'll draw it next week, I believe. So those are called dislocations. And the other kind of defect, or three-dimensional, are surface defects. So in metallurgy, we call a volume of the metal where all the atoms are all lined up according to their crystal structure without interruption. We call that grain. So a grain is a crystal. And when a metal starts to solidify from the liquid, different places in the metal start to solidify and they grow out from the center until they bump into one another. And each of them has a slightly different orientation to their crystal. They all have the same crystal structure, but those crystals are oriented slightly different. And when they come up to one another, there's a boundary between them. And all of the atoms on both surfaces are missing at least one bond. That's a grain boundary. That's the surface defect. They're called grain boundaries. And again, we'll talk about how you could manipulate grain boundaries to improve strength. Now I said permanent deformation happens when dislocations move, right? So we get permanent deformation or plastic deformation when a stress can cause a dislocation to move on a specific plane in a specific direction. the plane and direction where that would happen is different between BCC and FCC. Don't need to write that down. We'll talk about that a lot. But each of these defects, not vacancies, impurities and dislocations and grain boundaries are all obstacles to dislocation motion. So if we can do something that creates an obstacle to dislocation motion, essentially we're making the metal stronger, right? Because the dislocations can't move. If the dislocations can't move, then that stress isn't enough to cause deformation. It takes more stress. So effectively, we've made the metal stronger. So adding these kinds of defects, which are dislocation obstacles, means I need more stress in order to cause permanent deformation, which is the same as saying it's stronger. And dislocations repel one another. That's the reason dislocations are obstacles as well as the thing that moves. One dislocation will be an obstacle to another. So if I can add impurity atoms, well, that's just alloying. You know, that's just mixing two metals. So if I mix silver and gold, what I get is stronger than both, silver or gold, because one is the impurity to the other. It adds strength. If I could add to the number of dislocations, I make the metal stronger. And the number of dislocations increases every time we permanently deform. If I could add to the number of grain boundaries, I make the metal stronger. So that essentially means I need smaller grains. So there's more grain boundaries. And we'll spend the next few weeks just talking about how to do each of those things to make the metal stronger. All right? So that's an intro for crystal defects, and we'll get into each specifically. Let's take a break. That clock says 11:17. We'll come back at the clock saying 11:27. You made it.
Yeah, I gotta go to 11:50.
Oh, okay, sorry. All right. These aren't defects, but these are actually not directly something that strengthens a metal. But they're necessary in order to add impurities, and impurities do strengthen a metal. So vacancies, let's see. Number of vacancies. Let's say increases. Ends of B, that's the number of vacancies per this time we're using meters. Number of vacancies per cubic meter is equal to the number of places there could be a vacancy, which generally is the number of atoms, times E to the minus Q sub V over K T. K is Boltzmann's constant. I believe 8.1, 8.62. Electron, well, 8.62 comes down to negative 5. Electrons, let's use EV. Electron volts per atom degree Kelvin. T is absolute temperature. So if you have, X degrees C, then that's X plus 273 degrees Kelvin. So whatever your degrees C is, just add 273. And Q sub V is the energy necessary to form a vacancy. And electron volts per atom. I want to check on Boltzmann's constant. I think that would be better. What is Boltzmann's constant? See if she knows. Yes, it is a product proportionality constant. What's the value of it? What's the value of Boltzmann's constant? There we go. Joules. I don't know joules. Well, what's the value of Boltzmann's constant in electron volts per atom? 8.62 to the negative 5. Good. All right. So, in order to calculate the number of vacancies per cubic meter, I have to know the number of atoms. So I need an equation for that. So, the number of atoms per cubic meter got to be related to density, because that's mass per cubic meter. So if I have density in grams per cubic meter, I want to turn the grams into the number of atoms, so I could use the atomic mass in grams per mole. And now I can use Avogadro's number in atoms. And I'm going to want, density is in cubic centimeters, so I'm going to need to go 100 centimeters per meter cubed. And now I have atoms per cubic meter. As long as I know the density and the atomic mass, I can find that. So, let's see. So, let's see. given a metal with density of 6.02 grams per centimeter cubed, and atomic mass of 40.2 grams per grams per mole. And I need one other thing. Oh, yeah, activation energy Q's and B is 0.9. And that's electron volts per atom. Calculate number of vacancies per cubic meter at 500 degrees C and at 700 degrees C. So I need N first, and it's going to be equal to the density, 6.02 grams per centimeter cubed, and then 40.2 grams per mole. 6.2 times 10 23rd atoms per mole. Now I have grams cancel, moles cancel, atoms per cubic centimeter. So I've got 100 centimeters per meter cubed. So I'll multiply by 10 to the 6. 6.2, 6.2, 10 to the 29 over 42. So I get 9.02 times 10 to the 28. Atom locations per cubic meter. Number of places where there could be a vacancy. So N sub B then is that number times E to the negative 0.9 divided by 8.62 times 10 to the negative 5. And we're at 500, so that'd be 773 Kelvin. all of this is equal to 13, well, negative. Is that negative sign? Negative 13.5. And that's really the number of figs I should use. So I need negative that. E to that power, all of this together is 1.37. That's 10 to the negative 6. So I've got 1.23 times 10 to the negative 20, sorry, 10 to the positive 22 is the number of vacancies. So if I increase the temperature, just here's a guess, will I have more vacancies or less? Here's a clue. Materials or metals especially expand when you heat them up. Solid metals expand when they're heated, right? Thermal expansion. So if the number of atoms doesn't change, but it gets higher in volume, what's happening to the number of vacancies? It's increasing, right? This is the reason for thermal expansion. The creation of vacancies is what causes thermal expansion. And this number, that Q number, is your sort of determinant of the extent or magnitude of thermal expansion. Okay, so what will this be then at 200 degrees C higher? So N sub B at 700 C, got 9 times 10 to the 28. E minus 0.9 over 8.62 and then it is 5 times 973. This is a less negative number, negative 10.7. So e to that value (2.19) and the negative 5. So 1 point, actually closer to 2.0 times 10 to the 24th power vacancies per cubic meter at 200 degrees higher, 2 orders of magnitude greater. Now, another version of this problem is I could give you the number of vacancies. I could give you everything you need to calculate the number of atom locations. I could give you temperature, K is constant, and ask you to calculate Q sub V. And if that happens, if you get something like that, this form of the equation is really makes it complicated. It's, you almost have to iterate. So another way to write this equation is the natural log of n sub v is the natural log of n minus q sub v over kt. So I could give you n sub v. I could give you density and atomic mass to find n. And I could ask you to calculate Q. Let's do that, just so you have an example. I'm probably gonna have to make up some numbers, which could give us a really crazy Q. But, let's see. All right. Yeah, no matter what, we might get a Q that's way out there, but we'll do the method works. And that's what's important. So let's say, how would that be written? A metal with density equal to 9 grams per centimeter cubed, and atomic mass of 50 grams per mole, is heated to 500 degrees C, where the number of vacancies is, here's where I'm really making things up. Well, I don't want all these fives in here. Make this, oh, that's fine. Let's say number of vacancies is 4 times 10 to the 28 per meter cubed. All right, so I can calculate n. I have n of v, I have temperature, I know K. I can calculate Q. So, what is n? N is density, 9 grams per mole. Atomic mass, 50 grams per density, grams per centimeter. Two times 10 to the 23rd atoms. So I've got grams, cancel moles, cancel atoms per cubic centimeter. So this is 9 times 6.02 divided by 50 times 10 to 29. Oh, that shouldn't be so big. 10 let's make it 10 to the 22nd. Okay. 9 times 6. Divided by 50. So this is 1.08 times 10 to the 29 atoms or atom locations per meter cubed. All right. So natural log of 4 times 10 to the 22. Natural log of 1.08 10 to the 29 minus this would be over 8.62 times 10 we get 5 and we are at 773. So this number is electron volts per atom, K, and this is K. So Q will be electron volts per atom. All right, 4 times 10 to the 22. A natural log. 52.0. Equals 66.9 times Q sub B over that's a decent number. Actually, I'm getting number very close to 1. Check to see if you get the same answer. Q value should be right around 1. I've seen them as high as 3, very rarely. Usually between 1 and 1.5. Okay, so that's another version of the kind of question you might see. All right, so I've got in-class / homework due Monday. This time I have a box for you to put the answers in. You can show your work, I kind of recommend it, just in case you have an error. Make sure it's neat. If you want to do this collaboratively, okay, just turn in one with all of your names on it. Okay? Second one, finding crystal structure. The third one, finding the number of vacancies at a given temperature.
We've met.